Okay, we're in section 4.4, which is properties of definite integrals. So in chapter 4, the first three sections, we've seen indefinite integrals. We saw definite integrals. In the last section, we looked at the connection between antiderivatives and derivatives, or integrals and derivatives, in the fundamental theorem of calculus. So the next three sections, the last three sections of chapter 4 that we'll be doing, starting with 4.4, is all about computing integrals, period. So we need properties, and then in 4.5 we'll be looking at our first integration technique outside of just the power rule. And then in 4.6 we'll be looking at the first advanced technique of solving integrals, but that'll be the last technique that we study in this class. If you go on to a second calculus course, you'll pick up with where we leave off in chapter 4 with 4.6. So 4.4 we have three objectives. The first is to look at properties of integrals. And this is our big overarching integrals. This is our big overarching objective through the whole thing, so we'll be trickling these in slowly. Number 2 is to solve applied problems. And number 3 is a very specific application that we call average value of a function. So we've seen the definite integral, the integral from a to b of f of x dx. We can think of it as the area under f of x on the interval, the closed interval a to b. And so if c is a value in between a and b, we have our first property, which is the additive property of definite integrals. Now we did touch on this a little bit in the last section. So what this property says is that the integral from a to b of f of x dx, given that c is in between them, can allow us to split the integral a to c of f of x dx plus the integral from c to b of f of x dx. So we did talk about this before, but this is super useful, especially when we have piecewise functions, to split up our definite integral or split up the area under the curve. So if we take a look at this example, our f of x, we want the area underneath from -4 to 5. Our f is a piecewise function. So if we look at the integral from -4 to 5 of f of x dx, we want to split it right here at x equals 3. So this is the integral from -4 to 3. And when we are less than -3 or less than 3, we have 9 dx plus the integral from 3 to 5. And when we're greater than or equal to 3, we are x squared dx. So you can label both of these as parts 1 and parts 2 of our function. And so we split it at the breaking point of the piecewise function. If we have 3 pieces, we'd have 3 definite integrals. And then it's just a matter of calculating. So this is going to be 9x from -4 to 3 plus x cubed over 3 from 3 up to 5. So this is 9 times 3 minus 9 times -4 plus 5 cubed over 3 minus 3 cubed over 3. And that is a 5, I promise. And so we have 27 plus 36 minus 125 over 3 minus 27 over 3, or Why did I make this minus? That should be a plus. It's plus here, it's plus there. Or 63 plus 98 over 3, which equals 287 over 3. And that's our area under f of x from -4 to 5. Right, so it's just about splitting up properly our definite integral at the breaking point of our piecewise function. Okay, so if we turn the page here, a couple more integrals. Now I'll walk through this one. You should give this a try, but if you're still not quite comfortable with it, this is fine. You can work with me on it. So when we have absolute values, remember the absolute value of 1 minus x squared is a piecewise function. That is 1 minus x squared when this is positive, when 1 minus x squared is greater than 0, and negative 1 minus x squared when this is negative. So what we need to do is figure out what this is. So 1 minus x squared being positive, greater than 0, is when x squared is less than 1, or when x is less than 1, or x is greater than -1. Now, this matters because our limits of integration are 0 and 3. So since this doesn't appear in our interval, this becomes the split point of our limits of integration. So the integral from 0 to 3 of the absolute value of 1 minus x squared dx becomes the integral from 0 to 1. And at 1, when we're less than 1, we're positive. So from 0 to 1, we're doing the integral of 1 minus x squared dx. And then from 1 to 3, we're doing negative 1 minus x squared dx. And so we can think of bringing this negative out front. The nice thing is the antiderivatives for both of these are the same. So this is x minus x cubed over 3 from 0 to 1 minus, bringing that negative outside, x minus x cubed over 3. I guess we should put those in parentheses, from 1 to 3. And this becomes 1 minus 1/3 minus 0 minus, that's this minus here. This is 3 minus 3 cubed over 3 minus 1 minus 1/3. So you can put big brackets around these things to break it up to make sure it's clear. And when all of this gets evaluated, this is equal to 31 over 3. That's our area. Now the big thing here, takeaway, is how do you separate the absolute value? And so you have to look at when it's positive and when it's negative. It's not just the x value, it's the entire inside of your absolute value. So on this next problem now, it is a practice problem, so I recommend you try this one out on your own. So it's a simpler version of the one we just did, setting up the absolute value. So pause the video and work this one out. And I'll start walking through the solution now. So this is the absolute value of x, which is x when x is greater than or equal to 0, or negative x when x is less than 0. So that means we're going to be doing the integral from -3 to 0 of negative x dx plus the integral from 0 to 4 of x dx, because this is our split point. So this is negative x squared over 2 from -3 to 0 plus x squared over 2 from 0 to 4. So this is negative. We'll put that in big brackets here. 0 minus negative 3 squared over 2 plus, this is 4 squared over 2 minus 0. And when you simplify this all down, we end up with 25 over 2 as our area. So again, for both of these problems, the big takeaway isn't the actual calculating of the integral, it's the understanding where to split your limits of integration at. And you're always, for absolute values, going to be looking at where it's positive and where it's negative, because that's what our absolute value function is. It's piecewise. So, if we turn the page here, we're talking about the area of a region bounded by two graphs. So, if we want to find, as this paragraph says, we want to find the area of the region bounded by the graphs of two functions, f of x and g of x. So we're using this as our standpoint. We want to find this space here, this area that's in here. And we have to do it on a specific interval. So our interval is from a to b here. So what we look at is the area underneath f, which is just this line, and the area underneath g on that same interval, which is this piece. So notice that you can fit the entire area of f into the same location if we were to continue this graph and fill this in here. That white space now is what we want. So we're always looking at what's the top function and what's the bottom function. So g, over here back in our main diagram, g is the bottom function. Now when we say bottom function, we mean on the interval that we care about, what's underneath. And for us, that's g. And the top function is f. So these are the two big things. You want to identify the top and the bottom. And then, if we want this area, we take this big area and we subtract away this space. Well, that's the area under f minus the area under g. We know the area under f is the integral minus the area under g. And since they're on the same intervals, a to b and a to b here, we can combine this into one integral, a to b. And so that's what we have in this next box, the area between two graphs, sometimes called the area between two curves. So if f and g are continuous functions, and f of x is greater than or equal to g of x over some closed interval a to b, then the area of the region between those two curves from a to b is the integral from a to b of f of x minus g of x dx. Now, if you're not given the a to b, what we do is set f of x equal to g of x and solve. So if you're not given your bounds, this is how we identify our bounds, by solving when the functions are equal, because that will be when they intersect. That'll be how we find those 2 points. So let's take a look at a little example here. Find the area of the region bounded by y equals x to the fourth minus 3x cubed minus 4x squared plus 10 and y equals 40 minus x squared over the interval 1 to 3. So what you can do easily is graph the functions on your calculator to identify which one's on the top and which one's on the bottom. Right? We're not trying to make this too complicated, but if you plug these into your calculator real fast, you'll find that f of x is the top function, which is this first one, and g of x, the bottom function, is the second one. So this is our a to b, 1 to 3. So setting up our integral, we have the integral from 1 to 3 of, oh, I said this incorrectly. So g of x is actually the top function in this, and f of x is the bottom function. I said that backwards. And I got that just from graphing on the calculator. So you're just plugging this into your calculator, your graphing calculator, and plugging this in your graphing calculator, and you see that this g of x is the top. So if you want to label this one f and this one g, that's fine. All you really want to do is do the top function minus the bottom function. dx. That's what we're setting up. So for us, this is the integral from 1 to 3. The top is 40 minus x squared. And this will be minus the bottom, which is x to the 4th minus 3x cubed minus 4x squared plus 10. Goes in big brackets with our dx, our differential. And then it's just about simplifying. So simplifying this, we have the integral from 1 to 3, negative x to the 4th plus 3x cubed plus 3x squared plus 30 dx. And this becomes we're doing antiderivative. Lost my train of thought there, sorry. So negative 1/5 x to the 5th plus 3/4 x to the 4th plus x cubed plus 30x evaluated from 1 to 3. And so this is negative 1/5 times 3 to the 5th plus 3/4 times 3 to the 4th plus 3 cubed plus 30 times 3 minus negative 1/5 times 1 plus 3/4 times 1 plus 1 plus 30. And when you evaluate that all the way out, you end up with 97.6 as a decimal. Now, there is another way that we can figure out what the top and the bottom is, since we know our interval. So if we flip this over just on the back side here, so another way to determine the top and bottom this is aside from just graphing. So if a to b is the interval, pick a c such that a is less than c, a is less than c is less than b. So essentially you want to pick a number that's in between. So in our last problem there, we had the interval 1 to 3. So we could pick x equals 2 and then look at f of 2 and look at g of 2. And f of 2 being the first function is negative 14, and g of 2, the second function, is 36. And so 36 is bigger than negative 14, which means that g is above f. So that's another way to do this. Now this does have some issues. So graphing is still the best potential way to do this. But the issues that come up with this method is what happens when there are multiple intersections of the graph. Now, for most of our graphs, we're not going to deal with that, but just keep that in mind. So if you're not going to graph it on your calculator, you can always do this. And this is a faster method, a little bit, relatively speaking, than putting it into the calculator. So let's look at another practice problem. So it's practice, so I encourage you to pause the video and try this out. Identify what your top and your bottom function is. Now this one doesn't give endpoints, so going back in the notes, remember you have to set these equal to each other and solve. So I'm going to walk through this now. So our first step, set f of x equal to g of x. 2x plus 1 equals x squared plus 1. So 2x equals x squared minus 2x equals 0, x times x minus 2 equals 0. So x equals 0 and 2. So those give us our endpoints. So our interval is 0 to 2. That's what we'll be integrating on. Now to figure out the top, 2x and x squared plus 1, f of 1, since 1 is in between 0 and 2, is going to be 3. And g of 1 is going to equal 2. That means this is the top function, f of x. So when we set up our integral, we have the integral from 0 to 2 of f of x minus g of x dx, or the integral from 0 to 2 of 2x plus 1 minus x squared plus 1 dx. This is the integral from 0 to 2 of negative x squared plus 2x dx, which is negative x cubed over 3 plus x squared, evaluated from 0 to 2. And when you do that evaluation using the fundamental theorem, you end up with 4/3. So if you're not given the interval, set your functions equal to each other, solve those. Your x values will give you your interval. Now if you get more than 2, that means you have 3 different pieces, and it means you need to check what's the top and the bottom in each piece. So you could have multiple intervals from 0 to 2, 2 to 3, 3 to 4, and then you would have to check points in between all of those to see which one's on top and which one's on bottom for each piece. So, excuse me. In this next example, we're doing an application. So a clever college student develops an engine that is believed to meet all state standards for emission control, so a car engine. The new engine's rate of emission is given by E of t equals 2t squared, where E of t is the emissions in billions of pollution particles per year at time t in years. So the emission rate of a conventional engine is given by C of t equals 9 plus t squared. In part A, we want to know at what point in time will the emission rate be the same. So we are comparing the new engine versus the traditional. So we're comparing E to C. You'll notice here I've provided us a diagram, E of t. And so where they are equal, where they are the same is where they are equal, so we need to find that point. So we set E of t equal to C of t, or 2t squared equals 9 plus t squared equals 9, or t equals 3, and negative 3. Now since t is time, we can go ahead and eliminate this value, and we see that that matches up with our graph. So this is the algebra that dictates the graph. And what we want to know now is the reduction in emissions results from using the student's new engine. So The traditional engine, if we were to continue this straight down, would have all of this plus this area. And that would be, remember, this is total. So area under a curve represents total for that function. So this would be the total amount of emission for the traditional. And we want to know what the reduction is. So what we look at is the area in between. What I have here is orange, and this becomes the reduction. So we want the area between the curve. We do the integral from 0 to 3. Why do we choose 0, you might ask? Well, this starts at 0, at x equals 0, because we wouldn't go past to the negative because t is years. So from 0 to 3, we're doing c of t, which is the top, minus e of t dt. So this is the integral from 0 to 3 of 9 plus t squared minus 2t squared dt. And that's going to be the integral from 0 to 3 of 9 minus t squared dt. The antiderivative of 9 minus t squared is 9t minus t cubed over 3. And this is evaluated from 0 to 3. And so when all said and done, this is 9 times 3 minus 3 cubed over 3, and then minus 0. This becomes 18. And this is billion particles of pollution reduced in 3 years. Now, the question I get a lot with this particular type of problem is, why are we choosing the area in between? And the reason for that comes down to what our areas represent, our geometric areas. So if we break this up along E of t, the shaded region I have here in blue that I shaded, this is the amount, the total amount of emissions that the new engine will give off in 3 years, is this space. And so all of this orange is the amount that would have been given off in addition to this. So if we figure out what this area is, that's how much we've reduced it by, because we're not counting that anymore. It's above E of t. So it allows us to simplify the process instead of finding E of t and then subtracting. But that's exactly what we did. Right? We took the total and minus the blue part. And so that's why this orange shaded region is the reduction of emissions. So you always want to be thinking about geometrically, what do your areas represent, not just memorizing how to calculate. So turning the page now, we have our last little application, which is the average value of a function, and we're specifically talking about continuous functions here. So another important use of area under the curve, or the definite integral, is finding the average value of a function on a closed interval. So we've talked about that the area under the curve represents total T. All right, we just found total emissions. And so what we do then is we use the standard convention of dividing the total by the number of data points n to get your average. So T divided by n equals average. Now for functions, finding that n is a little bit trickier, but we do have the following theorem to rely on. So this is how we define average value of a function. So let y equal f of x be a continuous function over some closed interval a to b. Its average value, which we denote as y sub avg, over a to b is given by the total value of f of x divided by n. So total value of f of x over a to b divided by n. And we know the total value is the integral from a to b of f of x dx over n. And n is 1 over b minus a. So n equals b minus a times the integral from a to b f of x dx. And so this is our y sub avg, or the average value of our function. This equation. So you can put a little note here that n equals b minus a. That's how we figure it out. So let's try this out in this example. Basic one first. Find the average value of f of x equals x squared over the interval 0 to 2. So our average value of y is going to be 1 over 2 minus 0, b minus a, times the integral from 0 to 2, x squared dx. This is 1/2 the integral from 0 to 2, x squared dx, which is 1/2 times x cubed over 3, evaluated from 0 to 2. This equals 1/2 times 2 cubed over 3 minus 0, which equals 8/6, or 4/3 fully reduced. So that is our average value. So it's not a complicated formula to do average values. You just have to remember to divide by n. So the most common mistake is to forget that part and just do the definite integral. So if we turn the page here, we have our last problem of this section. And we'll be doing an application here now with average value. So a police officer pulls Reggie over for speeding, but Reggie thinks he wasn't speeding. He knows that he didn't see any police cars for at least 5 minutes after entering the freeway and was pulled 25 minutes after getting on the freeway, pulled over. So if we assume that in miles per hour t, let me say that with proper inflection, if we assume that in miles per hour, t minutes after entering the freeway, Reggie's speed is given by this function v of t, negative 1 over 200 t cubed plus 3 over 20 t squared minus 3/8 t plus 60, where t is less than or equal to 30. Determine if Reggie was actually speeding by calculating his average velocity. So first, let's talk about why we're using t is less than or equal to 30. So he enters the freeway. And he's sure that for 5 minutes, there were no police cars. And he was pulled 25 minutes after getting on the freeway. So there's 20 minutes where he's not sure of. So we choose 30 because we want to be less than, or we want to be more than what he's sure, but still not too far, because as we know, our rates of change as we increase the time interval change drastically. So that's why we're choosing less, or that's why we were given t is less than or equal to 30. So we want the average velocity. So we're going to do total velocity divided by number of minutes. And this is number of minutes that he was not sure. About police presence. Not sure about police. I can't remember how to spell presence off the top of my head. That's why I'm a math major. Okay, so total velocity we know is the integral from a to b of v of t dt. and it's going to be divided by n because that's average. So our velocity average is 1 over b minus a times the integral from a to b of v of t dt. And so we need to decide what a and b are. And since we're looking at the number of minutes that he was unsure about the police, that means we're going to start at 5 minutes because he's sure that for 5 minutes he saw no police cars. And then he got, you know how we get when we're driving on the freeway, a little bit tunnel visioned, and he stopped noticing. So this is going to be 1 over 25 minus 5 times the integral from 5 to 25 of our velocity function, negative t cubed over 200 plus 3t squared over 20 minus 3t over 8 plus 60 dt. So this is going to be 1 over 20 times, this is negative t to the 4th divided by 4, so that's divided by 800, plus t cubed over 20, because we divide this by 3, it already has a 3, minus 3t squared over 16, plus 60t, evaluated from 5 to 25. So we're using the fundamental theorem here. This is 1 over 20 times negative 25 to the 4th over 800 plus 25 cubed over 20 minus 3 times 20 squared, 25 squared over 16 plus 60 times 25, and this is minus negative 5 to the 4th over 800 plus 5 cubed over 20 minus 3 times 5 squared over 16 plus, run out of space, 60 times 5. All right, so the 1 over 20 is going to happen at the end of this. And when you plug this into your calculator, rounding off, we get 68.75 miles per hour. So now we have to interpret this. So this is an average. So this is his average speed, or average velocity. So if that's his average velocity, we can guarantee, because it's an average, there had to be some points that were less than this and some points that were bigger than this, because that's the only way we get our average, unless he was exactly 68.75 the entire time. Either case, speed limit on the freeway is 65. So we can be sure that he was speeding, at least for a little while. So if you've ever encountered what we call a speed trap, this is actually how they do it. They have a little program that the police officers don't sit and do this themselves, highway patrol. But what they do is they have someone that clocks you at the 5-minute mark, and then 20 minutes later they clock you at your 25-minute mark, and they see what your speed was and say, okay, here's your speed at 5 minutes in was 66, and your speed at 25 minutes in was 66, but they know what time you finished, how long it took you to get there, so they can calculate your average speed by the time it took you to travel those 20 minutes, because it was 20 minutes, or from that position, and see. And so speed traps don't actually catch you at the moment you're speeding, but what they do is they look at how fast you were going at this point A, how fast you're going at point B, and how fast you got there. So if I clock you at 5 minutes, or if I clock you and then 5 minutes later, my partner who's, 10 miles up the freeway clocks you as well, and we calculate your average speed over that time is 68.75, they're going to pull you over and say you were going 69 miles per hour. Because one, you were at some point, and two, you can't prove that you weren't because they have math on their side. Again, it's not a police officer sitting in a cop car or a highway patrol officer sitting in his car doing calculus. It's a program that they punch in. They say, okay, here's the license plate. Here's the time I got him. Here's his speed. And then the next person says, okay, I got the same license plate at this time. This was his speed. And the computer tells them, were they speeding? It's calculated like that. Obviously, we can do it relatively quickly on paper, so a computer can do it in seconds, fractions of seconds, and then they come pull you over. If you are only traveling the speed limit, there is a very specific time that it will take you to get from the first officer to the second officer. And that's how speed traps work. So the next couple sections are going to be techniques of integration, more advanced techniques than just power rule. But this is the end of 4.4.